vectors and scalars. What are the differences between the two? So stick around. We're going to discuss what displacement is, how it's different from distance, and a couple of other quantities as well. And we'll make like a direct comparison between scalars and vectors. We'll talk about what the fundamentals are basically. So let's say you're going from your house to your school, and there are two paths to it. The first path is a straight line, like a straight road that goes directly from your house to your school. And then the second one is, well, you have some corners that you have to take, and then you turn and turn and turn before you get to your school. Now, between those two paths, the shortest one is the straight one. A straight line is the shortest distance between 2 points. So we're going to talk about displacement and distance in this case. Distance, is just how far you have moved from your house and all those turns you've taken. We'll take all of those ones into consideration and just add them all up. That's the total path traveled by you. While displacement is just how far are you from your starting position. That's all we're concerned about in a specific direction. So displacement is concerned about, did you move eastwards? Did you move south? Did you move west? Did you move east? And all of that. Another one that we can compare is a case of speed and velocity. But we're going to talk about that in the next 2 or 3 slides. How are these guys different from each other? Vector quantities can only be described in terms of their magnitude and direction, while displacement, well, you can pretty much describe them in terms of the magnitude only. And you have some good examples here. You've got displacement, you've got velocity, you've got force, you've got acceleration. So we've compared displacement and distance. You know the difference now. And then speed and velocity, are they the same thing? No, they're not. But just based on what you have on the screen, you should know they're not the same. But let me break it down further. Let's say you have 2 cars. The first car, let's say car A, is moving eastwards at 5 meters per second, and car B is moving westwards, still at 5 meters per second. If you're to describe them in terms of their speed, you would say they have the same speed. Yeah, 5 meters per second. But can we say they have the same velocity? Nope. And why is that? That's because they're moving in different directions. So once you start taking directions into account, then you move from talking about speed to velocity. Same thing occurs with distance and displacement. Once you plug in the idea of direction, then you're talking about displacement in that case. Another scenario is you have a track, right? The entire track is usually 400 meters. You run from the start to the end. The end is also your finish line. So if you run around the track, that's you covering 400 meters in terms of distance. But in terms of displacement, what have you got? 0, because you're back where you started from. That's another way to look at it. We also have an issue of mass and weight. Mass is typically the amount of stuff in an object. So it has the unit of kilograms, or 4 grams, 5 grams, 20 grams, 70 grams, and all of those things. You cannot say my mass is 70 grams in this direction. It's not possible. That's why it's only a scalar quantity. But in terms of weight, weight is a vector quantity. Weight is mass times gravitational field strength. Now, your gravitational field strength is a vector quantity acting towards the center of the earth. So once one of your variables is a vector quantity, then the entire derivative is a vector quantity. Once gravitational field strength is a vector quantity, then that makes your weight a vector quantity. It acts downwards. And how do we show the direction of vector quantities? Just by using arrows. So you have the typical examples here: 5 kilometers due east in terms of displacement. You have 30 meters per second due north, east, west, south, and all of those things. First, you can say 100 newtons downwards, 100 newtons upwards. Acceleration towards the earth, 9.8. Sometimes we round it up to 10 meters per second squared. Momentum, Yeah, for momentum is basically mass times velocity. I remember what I said earlier, and that is once one of your units in that equation is a vector quantity, then the entire thing, your derivative, is a vector. So momentum is mass times velocity. Velocity is a vector quantity. That makes your momentum a vector quantity. So we have positive momentum, negative momentum. Moving on, scalars are only concerned with the numbers, not which way. Distance 5 km, speed 30 meters per second, mass 50 kg, time 10 seconds, energy 100 joules, temperature 25. You cannot say, oh, this is my temperature. You cannot say, this is my temperature. My temperature is 30 degrees in the east direction. No, it's not possible. All right. Now, the arrows we use in representing vectors, there are a few rules that you have to keep in mind. The first rule is the direction of your arrow shows the direction of the first or the direction of your vector, and the length of your arrow shows the size of your vector. So if you have a 4 Newton first and an 8 Newton first, the 4 Newton first, the length of that arrow should be half of the length of the arrow for 8 Newton first. So that's what you should have on the screen. Yeah, this needs some little changes, but you get the idea. If this 4 Newton first, if you're to draw it, let's say you have 4 centimeters to represent 4 newtons. In order to represent 8 newtons, the length of that arrow has to be 8 centimeters. You get the idea. So the longer the arrow, the greater the size of your vector. And here, yeah, this is just basically what we talked about. 15 Newton first, you can say, oh, I'm going to represent that with 150 millimeters arrow length, and then 12 newtons, you pit that as well against the corresponding millimeter length, which is 120 arrow length. All right, so the 15 Newton first will obviously be greater than the 12 Newton first in terms of length. Basic things we need to remember. Number one, displacement is distance in a given direction. Vector quantity has both magnitude and direction. Scalar quantities has just magnitude, no direction. And then vector quantities can be represented by arrows. The size of the arrow shows the size of the vector. The direction of the arrow shows the direction of the vector. And remember, scalars, we do not talk about direction for scalars. Here are some quick questions for you to answer. So you can do well to pause this video and try to answer them. Okay, now let's check what you have done. First one says, is temperature a vector or scalar quantity? The first question you ask yourself is, can you describe temperature in terms of direction? No. So it's scalar. Question 2. What two things does a vector quantity have? Magnitude and direction. 3 says, how do we represent vectors on a diagram? Well, we do that by drawing arrows. The length of the arrow corresponds to the size of the vector. The direction of the arrow corresponds to the direction of the vector. So longer arrows means greater magnitude of our vectors. 4. A student walks 10 meters north, then 5 meters east. What is the displacement? All you need to do, take your ruler and then draw an arrow northwards 10 centimeters. At the base of that first arrow, that is vertical, draw another one pointing it to the east and represent that with 5 centimeters length. Once you do that, join both ends, the open ends. Join them together. That's like the hypotenuse of your triangle. Use your ruler to measure the length of the hypotenuse. That's your displacement. And convert that to meters. So let's say if you have x millimeters now, or x centimeters, if you're using centimeters, you just convert that to meters. All right, you get the idea. And then 5 says, give 3 examples of vector quantities. If you are not able to answer this, you can easily just go back. We've listed quite a number of vector quantities, your force, acceleration, displacement, momentum, and a couple of others. So that will be all, and I'll see you tomorrow.